This week is the last week of classes. All right, you guys with me? Next week, what happens? Finals. Every schedule changes a little bit. Our final starts 9:25. What day? Yeah. So am I going to see you at all next week in here? Nope. Does everybody understand? Next week, nothing is happening in this room for us. Right? Next week is finals. You don't come and see me again until final. Or if you see me in the message, then you'll see me. But we won't see each other here. Is everybody with me? Next week, you do not go to your normal class time. You go to your final exam time only. Because next week is finals. Does everybody understand? Any questions? It's okay. Any questions? What's up?
Is that for all classes or just
All classes.
Oh.
It's not my decision. So I really want that to make sense. Are there some classes that meet for like about an hour? Do you guys know? Are there classes that meet for about an hour?
Yeah.
Yes. How long does every class get for a final exam? Do you know? 2 hours. Every class gets 2 hours. So wouldn't the schedule have to like change? Right? So what if you're in a room that there's a class in before you and they get 2 hours, you can't meet. So next week is just finals. Next week and Monday, right? Because next Monday is holiday, Memorial Day, right? Yes?
If we want to like talk to you, is tutorial, if we want to turn on the laser or we want to talk to you, do we like tutorial or where do we go?
Yeah, just come to my office. Yeah. Oh, right. Everybody's got my updated office hours for, and of course this week is normal. Right. This week is normal, so you can come see me. Normal office hours. On your grade sheet summary, I've got the little box with my finals week office hours. Right. Where I'll be. Right. And you can see our final up there, just for another final reminder. Okay. Please do, any questions about how any of that's going to work? Okay. All right. And let me know if there's a conflict. Sometimes teachers go rogue and they just decide to do their final whenever they want to, and then it conflicts with my time. I'm like, screw them. So just let me know if there is a conflict. Normally, the last Monday there won't be a conflict because most teachers, when they go rogue, they do the final earlier, right? Okay. All right. So we got one last section that you are officially responsible for. There's the homework again up there. For those of you playing the home edition, there it is. Okay, you could pause that thing. It's crazy. I really wish my teachers would have recorded the lectures. It would have been so much easier. All right. So this last section, if there's no questions from homework or anything, okay, this last section will be remarkably nice. Not just because I only assigned 4 problems, but the idea is really crazy straightforward. And you're all like, I don't trust your evaluation of what's straightforward, Jeff. I understand. So say I have a function, a nice continuous and differentiable function. Right?
And what does that say? Like that for next?
Continuous and differentiable. I'm sorry, I'm not calling it something. Yeah, not a see you next Tuesday. No. Little jerk function. All right. So let's just say from A to B, right? So we got A to B. We got this function, nice continuous and differentiable. What we're about to do would actually work if it wasn't strictly continuous. We're just going to make it continuous, just to make it easier. So what I want to know is something different than what we've done. I want to know how long that line segment, that curve, how long is it? How long is it? Yes? That's a very different question than we've ever answered before. But isn't that an important question to answer? Yes? If this is the trajectory of some rocket, and I only have so much fuel in it, don't I want to know how long that is so I know if it's going to make it? Right? Okay, that's just one quick example off the top of my head of why it would be important. So I'm given this function, and I want to know how long that line segment is. If it was straight, that would be simple, yes? In fact, let's all remember. What if I had a straight line from, let's say, get out of there. I'm just going to put the points. From 2, 1 to 4, 3. And somebody tell me how long that line segment is, especially the ones that were shaking their head. Yeah, that'd be easy, Jeff. This is easy.
One. No.
It's not that easy.
Oh.
This is what I want, yes?
Yes.
This is what I know, yes?
Yes.
So the distance formula is just Pythagorean theorem, right? So what would the distance here be? Well, d squared would equal, how long is this? Yes, it's 2. And how long is this? Also 2 just happens to be, right? Does everybody see where those are coming from? Difference in the x's, difference in the y's, yes? So this is like delta x, and this is delta y. So if I divided those, I would get the slope, but that's not what I want here. I want the length, right, of this segment here. So that would be d squared equals 2 squared plus 2 squared, right? So the distance would be the square root of 4 plus 4, square root of 8, 2 rad 2. All right, stop. Is that right? That's simple. Same way when we first learned integration, if it was just a straight line, it would be a stupid area of a triangle. Yes? If I asked you this question, find the integral from a to b of this, it's like, well, that's the easiest shit. I don't even have to use calculus. So here, I don't have to use calculus to figure out that line segment's length. I don't have to. What about here? Can you do that here? All right, you ready? The answer is yes. But we do it, of course. Where is this function linear anywhere? If it's differentiable, exactly, that's exactly the idea. Isn't it locally linear because it's differentiable everywhere? So if I take, I'm going to blow this up in a minute, but if I take a little dx, get in there. And let's say this is x1. Dx, oops, this is dx, and this is dy. Don't worry, I'm going to blow this up. So this would be the length, dl. I want this to really make a lot of sense. That's just a little piece of the length, yes? So dl means a little length element. So let me blow that up. If I just look at that region, I've got this, right? That's the curve. And I've got my dx, and I've got my dy. This is really zoomed in, yes? And of course, I'm representing an infinitesimal length with something that's not infinitesimal just because I can't draw an infinitesimal length. So you gotta excuse me. Okay. Is everybody with me so far? You guys with me? So locally, this is approximately linear. And in fact, if I make this smaller and this smaller, then it really becomes, just like Angel said, you zoom in, it becomes a line, basically, like the surface of the Earth, which is why some poor fools think it's flat. Locally flat, locally linear. I love it. Is everybody with me so far? So can somebody tell me, please, what is DL? Same thing, right? It's the square root of, say again?
dy squared.
Yeah, I'll do dx squared plus dy squared. It's the exact same formula we used over there, yes? Just instead of deltas, I have d's. Stop. Let me pull this up here. So dl equals the square root dx squared plus dy squared. All right, now so far I'm hoping, I mean that's pretty freaking nice. We know what to do if it's a straight segment. Isn't it a straight segment if I zoom in? so that I can just take each of these segments. What am I going to do with each of these segments to get the total length? Add them up, right? But they're all infinitesimal. So what is add them up when there's infinitesimal and an infinite number of them? No, integral. You can bypass the sum shape, right? So I want to integrate this from what to what? A to B. Crazy. Now what's missing here? Something's missing that a lot of you guys kind of just forget about anyway. Yes! Isn't that missing? And shouldn't it be dx? How do I know it should be dx? Because everything's happening in terms of x, yes? So I could do this whole thing in terms of y, couldn't I? Of course I could. Nah. Okay. This is, all right, I really want you, isn't it just Pythagorean theorem? Isn't it? We just zoom in enough so I get a nice straight line, and then I got Pythagorean theorem, who cares? And then I add them all up. That's a remarkably simple idea. Zoom in, little line, little line, little line, little line, little line, and you just add them all up. And then of course I get the whole length. Yes, of course I do. But there's something wrong, it's not gonna work. The calculus is not gonna work unless I have that dx at the end. So what am I gonna do? I'm gonna freaking take a dx out. Let me see if you guys are cool with this. Help me out. Let me do this inside. If I take a dx squared out, this is 1, yes? Why is that 1? Right there. Why is that 1? If I take a dx squared out, is everybody cool with that? I'm just taking a dx squared out. Don't worry about this yet. But why is this 1? Because dx squared divided by dx squared is 1. So what happens here?
dy squared over here.
Yes. And can't I write that like this? All right, let me stop. This is the weirdest part of this whole thing. And it's just a little bit of algebra. When I take something out, I divide it out. What's dy dx? In reference to this? What's dy dx in reference to this? Come on. What's dy over dx? How else can I write that? True. So how else can I write that in reference to this? I could write dy dx. Or I can write f prime. Isn't that just the derivative? All right. What's this integral? L. Is that cool? If I add up all the little lengths, I get the length. That kicks ass. And again, if you just use, screw it. I'm not going to too much. So watch this. What's the square root of dx squared? Square root of dx squared dx. Okay. That's the formula for the arc length. Or the length, we call it arc length, of course, but the length of a curve. Will it work there? Yes, it will. Yes, of course it will. All right, help me out. I erased it, of course, because I'm crazy. But I want to go back to the line segment because I'm telling you this method works, period. If I have a continuous and differentiable function, is a line continuous and differentiable? Yes, right? We got it. All right, so remind me, the length, the arc, let me try it again. The segment I gave us went from, what was it? I shouldn't have erased it, but I won't. Went from what to what? Somebody write that down?
2, 1, 2, 4, 3.
Say again?
2, 1, 4, 3.
4, 3, okay. Now, all right. Now listen, the calculus on this example will be worse. The same way the calculus on a triangle is worse than just frickin' area of a triangle, correct? But I'm just doing this to make sure we get the same answer. If we don't, we throw the whole thing out. So we got, as an answer, was it 2 rad 2? Okay, so help me out. Can somebody figure out what the function is? How would you do that? So it's just y, right? y minus y1 equals m times x minus x1. What's the slope? 2 over 2, right? So it's 1. Y minus, and pick either point. Yeah, it doesn't care which point you want to use. 2, 1. So y minus the y piece equals x minus the x piece. So I get y equals x minus 1. Doesn't that work? Is y 1 less than x here? Yes. See how you can check it real quick? So that's my f of x. What does this need? Need to throw into it. F prime of x. What's f prime? 1. Right? And where am I going from to? 2 to 4. Square root of 1 plus 1, right? Dx. Now, why are you not concerned? What is this? Is it a function? It's a constant. So what's the integral of a constant dx? What's the integral of 3? 3x, right? Don't worry about the plus c because it's definite, right? But what's the integral of square root of 2? Square root of 2 times x from 2 to 4. So I'll get 4 square root of 2 minus 2 square root of 2 is 2 square root of 2. Why is that important? Why did I put a little exclamation mark after it? It's the same thing we got before, yeah. Okay, and again, I always get somebody who's like, well, why don't we just do this? Because we don't always get a straight line. We get this curvy shit. This will work for anything. That approach will only work if it's straight. So of course we did one that was straight so we could check it. So now I trust in this a little bit more because at least it came up with the correct answer. Okay, maybe? Maybe. Now, I picked those specifically, and man, I really hope I looked at them right, because there are, can we, all right, what if I had this? What if I had, let me give you one we cannot currently do. F of x equals x squared from 1 to 2. That's pretty simple, right? It's not a straight line, it's a little curvy, yes? Seems like it should be pretty simple. Well, let's try to set up what we need, right? Let's try to set up what we need. What do I need? So the length will be the integral from a to b, f, yeah, square root 1 plus x prime dx, right? And of course I could do dy if it was all in terms of y, same way. What do I need in there? Derivative of f, so what's f prime? 2x. And what's f prime squared? 4x squared. So I get the length is the integral of 1 to 2, square root of 1 plus 4x squared. Can anybody tell me why that is the problem we cannot do? You cannot do that problem right now. Do you see why? Why?
In the square root. So, and it's like an x squared.
What would you try to use here? What method? The only method we know besides normal integration is use of. Is the derivative of the inside out here. I would need an x out here, wouldn't I? So that's all it took to be beyond our ability. So it kind of sucks. We can integrate a lot of stuff, but there's a shit ton more things we cannot even begin to think about how to integrate. And this is one of them. Okay. Do you guys understand? That's why I couldn't give you a bunch of problems, because it relies on stuff from chapter 7 to do. So, okay. Just real quick, if anyone is curious, is anyone curious how you would do? Anybody? Yes? Okay. This one's a little bit funky. Let me see. All right, let me tell you. That one's a little bit gross. It'll work the same way. So if I had this instead, I'm going to make one little change. If I just had this, and then it's easy to bring the constant in, right? Watch this. If I make x tangent beta, you would never think to do that, yes? Can somebody tell me the most basic trig identity? What's the most basic trig identity? Sine squared plus cosine squared equals 1. If I divide all those by sine squared, I get 1 plus tangent squared equals secant squared. Yes? Did I say the right thing? Divide by cosine squared. There you go. You get 1 plus tangent squared equals secant squared. Does that sound familiar at all, that identity? Do you see how this is 1 plus something squared? So if I make x tangent, I get a trig identity in there. So then dx would be what? Now this is even going to still lead to something we can't do, but oh well. It's just to give you an idea. So then watch this. This is cool. I'm not going to worry about these yet. This would be the square root of 1 plus tangent squared. And look at this, is kind of nice. We're not used to this. I can just replace dx with this. What's the square root? What's 1 plus tangent squared? Secant squared. Square root of that is secant, so I get the integral secant cubed. Now that one we still, and I haven't even done this. Anyway, I just want to show you real quick. This would still require some extra shit, but this idea of trig sub is one of the very first, it's not the very first, I think it's the second thing you learn in Calc 2, if you take Calc 2, is this thing called trig substitution, right? So if it would have been 1 minus x squared, I would have done sine. Because what's 1 minus sine squared? Cosine squared, and that simplifies a lot, yes? But this is really weird. You would never necessarily think to do, why the hell would you bring tangent in out of nowhere? Well, just because it makes this a nice identity. Okay, that was more than you needed, but. So let's try a problem out. Let's see. I'm gonna pick one out that we can actually handle at this level. Oh, I see, they do that. That's evil. Let's do one we could do. Barf. That's barfy. All right, let's do this one. Yeah. Yeah. This is good that we're doing this example because I gave you one problem in the homework. One of those 4 is like this. All right, let's see. So I want to know the arc, the length, and let's go from 1 to, sure, let's go from 1 to E. So what would it be? From 1 to E. So at 1, what is this? Just out of curiosity, at 1, what is this? What's the natural log of 1? 0. So it's just 1, right? And at E, what is this? Good. So I definitely don't want to do dy. I don't want those gross things. I just wanted to get the points just because. Okay, let's all take a breath. So this would ask me, from x equals 1 to x equals e, what's the length of this curve, right? Whatever this thing looks like. So I need, let me write down the basic idea. So I need, of course, f prime, and then I'm hoping that the inside of that somehow simplifies a decent amount, right? Let's see what happens. Is everybody with me? So this is the idea, right? I'll probably give that to you just because it's incredibly brand new if I put a problem on the final like this. So what is f prime?
2x minus 1 over 8x.
2x minus, good. So 1 over 8 times 1 over x, 1 over 8x. So what is f prime squared? Because that's what I really need here, right?
4x squared minus 1 over 64.
Good. Well, let's see. Let's do this. Let's be careful. Yeah. So this will be 4x squared minus 1/4 minus 1/4. Is that cool? 2 times 1, 8, right? Minus 1/4 minus 1/4.
Minus what?
The x's cancel too, right? Is that, sorry?
Wouldn't you add them? They'll both be negative.
Oh, sorry. Yeah, minus, exactly. Minus, the x's cancel though, right? You guys see? 2x times 1 over 8x, the x is canceled, the 2 and the 8 reduce to 4, so 1/4 minus 1, negative 1/4 minus 1/4 is, negative 1/4 minus 1/4 is a half, so minus 1/2. And then at the end I get
64x squared. Positive.
Does that look promising? Oh, I like it. Somebody's saying yes. I love it. Okay. And of course, so let's see. Let's throw it in here, see what happens. So it's going to be integral from what to what? 1 to e, because everything's x, right? Square root of 1 plus 4x squared minus 1/2 plus 164 x squared dx. So then again, this is kind of nice. It's a construction problem. It needs f prime. Let me make it. I've got to square it. Once I get that, I throw it in, and then I kind of hope. So I get 4x squared plus 1/2. Is that cool? Plus 1 over 64x squared. Okay, let's see if you guys are cool with this. I cannot handle that square root staying there. Especially not this problem. You guys understand? If this was it, if this is all I could do, we can't do this problem. Because if I make u equal to this, that's definitely not what it needs. It needs a lot. Holy shit. So what I'm hoping is, see if you guys see this. Do you guys see how that's quadratic in form? Maybe? Maybe? So watch this. I can actually factor this thing. So this would be 2x. See if you guys are cool with this. So that's, let me cut this in half. 2x, let me cut this in half. What would this be cut in half? Multiplicatively there. 1 over 8. 1 over 8. And I'm claiming that's true. Let's see if that's true. We kind of know it's true. Do you guys see how we know it's true? If these would have both been plus, wouldn't this have been plus 1/2? So that is true. And then what happens? Thankfully. So then I just get integral 1 to e, 2x plus 1 over 8x. And that's easy, right? Yes?
How did you get the plus 1/2?
Here?
Yeah.
Right here, 1 minus f, right? Just putting your like terms together.
Okay.
So this is the 1 plus f prime?
Yeah.
Yeah, and then you hope that something happens. So it has to be a very special kind of function for us to be able to do this, because it has to come out so the square root cancels or something, right? And then this is easy, I'm not going to worry about it. Right, this would be x squared. What would this be? Be better. Isn't that 1/8 1 over x? So integrate that, isn't that 1/8 natural log? Don't let the 8 come in all in this. You don't give a shit about constants. So this will be 1/8 natural log of x. It would be absolute value, but I know it's positive, so who cares? And then you just throw an e in and 1 in there. Blah, blah, blah. Crazy.
It's kind of weird how close it came.
Yeah.
I know, it's neat. Yeah. That's sort of why I did the points there, because now it's almost the same, but it was minus instead of plus, yeah. Now that's just a coincidence. Don't think that every function is going to be sort of the same. Okay. So hopefully, all right. So I know how long will we work with that idea? 15 minutes maybe, right? But it's relatively simple compared to some other shit we've done. There's no rotations or anything. The idea, this sort of lost the idea a bit, but the square root with a square tells you it came from Pythagorean theorem, because we just zoomed way in and we got a little tiny triangle, and we know what to do with a little tiny triangle, little right triangle. So putting this together was actually relatively easy, hopefully. Right, if you look back, we just did Pythagorean theorem. We did a little weird thing to get this guy out there, but we know we need him out there. So we just did what we had to do to get him out there. I like it. So, I'll just say a word or two about section 8.2, or maybe several words. They kind of go through the derivation, but it's a lot like, how do I say this? Oh, all right. All right, I'm not going to assign any homework from this, so that might make some of you guys just sort of take your phones out and start looking at Google or Instagrams or something. But, real quick, this is kind of nice. If I have a line segment, I can rotate that line. I can rotate that line segment. And then I would be curious about what's the surface area of the thing that I just created. Now, why am I not making a volume? Because this is just a line. It's not a region. I'm not going to get a volume. Yes? If I rotate this, I'm just going to get this thin shell of something, right? So if I rotate this, yeah. I'm going to see if I can do this. That's pretty good for me. All right. Or is this the, I don't know. Sure. Something like, okay. I don't know, something's wrong with that, but right, I get this thing. So not surprisingly, it's the circumference that matters now. What's that circumference gonna be for like any of these? It's gonna be 2 pi r, right? That's the circumference of the circle I've made. And then I basically just multiply it by the length of this thing. It's kinda, that's a little silly. Yes?
Well, why by the length if it's like a regular shape?
Oh, okay, so it's like the little DL thing again, right? And then that's why it's gonna lead to have this. So if I do so if I get a little segment, a little DL element, then it's straight. So I'm glad you said that, so that's what kind of builds up. And the function comes out to be exactly what you might think it's gonna be. 2 pi x square root of 1 plus f prime of x dx. So this, and this is what that would lead to, yes? Like we just saw. So that's why obviously A2 builds right off of A1. But again, it's sort of, I didn't want to throw another rotation thing at you. I think we've done enough rotations, right? But this is a relatively simple rotation, but the problem is, well, now it's a lot easier for us to have, because now there's an x there. So if I have an x squared inside, wouldn't u sub work? Okay. That's all I want to say about section A2. It's another rotation, but now I'm just rotating a segment, so I just get a surface area, not a volume. So yeah, there's no homework from section A2. So what I want to do now is I want to see if anybody either wants to do another problem from A1 or wants to maybe start looking at the practice final or has more questions from the test. In fact, some people didn't get the test back yet. That makes sense. You got a practice final in it too, right? Everybody else got their, yeah. Oh, that's not bad. Okay. So we have a few minutes, so if you have, yes,
Number 3.
on the test,
Yeah, my practice final.
practice file. Yeah.
I forget power, acceleration, and all those things related.
Oh,
Composition.
I can actually try this because I just remember this. So if I remember correctly, you have position and then you have velocity, which is the derivative of position, and the acceleration, which is the derivative of velocity.
yeah, so if I give you a position function, the second derivative is the acceleration function. Yeah.
And the derivative, or the integral of velocity would be acceleration.
Then you can just go, well, no.
No.
So it goes S,
It's like position, velocity,
yeah,
acceleration.
ds dt is velocity, dv dt is acceleration. So if you want to go backwards, v would be integral, s would be integral, right? Right, if you go derivatives one way, you go integrals the other way, right? And why does this make sense? Because the velocity is obviously a change in position over time. Change in position over time. Acceleration is change in velocity over time. Yes? Change in velocity over time.
You guys are very positional at the end. Is that you guys?
Well, sort of. So, let me think. What's a good example of that? There's these weird little situations you would want to do that. I don't know, off the top of my head I can't think about it. It doesn't necessarily, there's not a word for it, you know what I mean? There are certain problems where doing that would make sense, but they're a little weird, so off the top of my head I can't come up with one. Yeah.
What is it called if you take the derivative of acceleration?
Does anyone remember? Did I tell you guys?
Oh, that's it's called like
Jerk.
yeah.
Yeah, which defined my first car. Here we go. I'm good. I'm good. So that's when your acceleration changes, and the more it changes over time, the bigger the jerk, which physically makes sense, right? Because you jerk when you right? Okay. So it's kind of good that they call it a jerk. What's the derivative of that? It's the change in jerks over the change in time, which I think right now is positive. Oh.
Change in jerks, change in time. I thought that was just called school.
Isn't it called like pop or something?
Pop?
Pop, something like
That
that.
sounds familiar. I don't
know
know.
that there was like snap, crackle, and pop or something like that.
Oh, maybe, because that, I don't know. I don't know if I was ever told that, but for some reason that sounds familiar. It sounds like I would have made a joke about that. Yeah.
Next semester, will we have to do imaginary numbers, or is that the semester? Or do we ever do imaginary numbers?
The calculus 1, 2, 3 series
Yeah.
focuses on real stuff. There will be imaginary elements happening. There could be in Calc 2, depending on what your teacher does with sequences and series. And Calc 3, I don't think so. Calc 3 deals with multivariables. So as far as I remember, we only try to stay with real stuff. It's been a while since I taught Calc 3. But we deal with real stuff because we're trying to just to figure out how to deal with X, Y, Z all at once in an interval, triple integrals and all kind of crazy shit. Off the top of my head, I don't think there's complex numbers in there. There's whole math courses devoted to kind of redoing earlier stuff, introducing the idea of complex numbers. So there are certain intervals you cannot do straightforward, but you can do them in the complex plane. And that's all I'll say. It was like, stop. It's really neat. You do it in complex plane, they just take the real part, you're done. But that's all I'll say. Yeah. So anything else? Did you, now again, we have review on Wednesday and review on Friday. I've opened it up to other calc classes, so we might have some unfamiliar faces join us if they want to come out this early. I doubt we'll get many, if any, because it's a little early for some people, not for us. So we'll see. If you see anybody different out here, then that explains that. And I think I'll bring the answer key for the practice final. I might bring it Wednesday. We'll see how I'm feeling.
Is the math lab open all the way till Monday?
Yeah, we're gonna have the same hours. Yeah, same hours next week, but the tutor schedules themselves might change. So if you know when a certain tutor is in there, that might not be true finals week. Yeah, but some tutors weren't able to tutor next week during their normal hours. So, because of course their finals are getting all over the place too. So yeah, so just be a little careful. If you're like, I love this guy, where is he? Taking a final, leave him alone. That's all I had, guys. So this is getting real now. We're almost there. And you all have kind of a target. And I might just go ahead and reprint out the grade sheets now that I think about it. I showed you the targets, but I might reprint them so you have them all to look at. And real quick, is it true that nobody except one person did quiz 1 and quiz 2 corrections? Is that true? Did anybody do quiz 1 or quiz 2 corrections? All right.
I think I'm minus number 2.
I think
Sure. I did quiz one
I
correction.
got something wrong.
But you turned them in physically to me, I'm guessing, because they're not on Canvas, because those first 2 quizzes we did on Canvas.
Yeah, I did.
Uh,
Oh.
But yeah, just double check. I might have given back the correction and it just never got in the spreadsheet. I mean, I'm human, that happens sometimes. So if you did do corrections, just bring them with you on Wednesday and I'll change it in the spreadsheet. Cool. All right.
I'm on.